I will talk a bit about how we have been using machine learning in the context of dynamic aperture studies. And this was a work in collaboration with Massimo Giovanotti, Ewan McLean, Carlo Emilio Montanari, and Gianluca Valentino. Gianluca already gave a presentation here about a part of this work. I think it was in October somewhere in the OWLE series. Okay, so first maybe a short introduction on dynamic aperture to give an idea what we're doing. So dynamic aperture is a mathematical tool that is used to estimate the beam quality. Now, the important points for us here are that its evolution over time can be estimated with scaling laws. We have analytical laws to evolve dynamic aperture over time, which is important for our estimates because we are limited by CPU time. And let's say it is used to estimate beam quality, but what it can be describing is the beam losses and luminosity evolution. These are two practical, let's say, observables. The two applications that we did in the last 2 years is detection of anomalies. So this part has been mainly already presented by Gianluca. I will briefly go over it. And the extrapolation of DA. So we have the scaling laws, but they are not perfect. So we looked for ways to improve actually extrapolation efficiency. Now, as most of you probably know, that extrapolation in machine learning, it's the here be dragons part. It is not trivial, but new technologies, new methods, and a smart approach of existing methods actually allows for some improvement in extrapolation. So definition of dynamic aperture, it is defined in the phase space. So it's the smallest connected region in phase space that is stable for a given amount of time. So we look at the evolution of space, the phase space, and we look for the stable orbits. What we typically do when we do studies, for example, for the Large Hadron Collider, is we make random realizations. We call them seeds, 60 of them, to have different possibilities for the errors that we expect in the magnetic inhomogeneities, in the magnetic field qualities. We do this in a polar grid. So we scan in transversal plane over an angle and over the radius. So then actually the reason we do this polar is that we can actually scan up till the moment where a particle is lost, let's say out of stability region, and then we consider this the zone of stability. That's important to do it this way because we want to cut out possible islands of stability because we really want the smallest region. So then we have two observables, the average and the minimum. The average would be the average over the seed. So we make an integral over the angles to get the surface. In practice, we integrate, of course, 6 dimensions, but since our initial conditions are only transversal, we need a single integral, and we make the average over the seeds. The minimum is really like the absolute minimum. It's the minimum angle of the minimum seed. This is some worst case scenario. Of course, this is statistically less stable, but it gives you an idea about what is the worst possible. So this is some picture of typical dynamic aperture. This is the polar plot. So the horizontal and the vertical directions, this is the transversal plane, and all the different dots are the stable borders for the 60 seeds. So then here the red would be the average over the 60 seeds, and or let's say the integral, the average of the 60 seeds, taking the integral over these angles will then give what we call the average dA. Taking the smallest of the minima, which is this one, will be the minimum dA. Okay, so the first part, anomaly detection. It can be that one seed gives a very bad dynamic aperture for one specific angle. Now, this is not numerical error. This is, let's say, this is physics because we're close to resonance or we have some internal cancellations. But we don't want them in our simulations. Why? Because we would not reach these in practice, in operation. When we see this happening, we would move away from it, let's say. So this is not representative for the possible beam quality. So we want to get these very bad seeds out of it. Why? Well, because they will dominate, especially this minimum dA, and then we have a wrong picture. It can happen quite a lot. And if one like me does a lot of studies, it's quite tenuous to do this manually in all the studies, get all these outliers out. So we tried using machine learning to flag the outliers. Now, what is important, at least for us, is that we don't want machine learning to act. We want to flag them and then let the human decide whether or not to remove them. So there is still some human verification. Now, of course, we want machine learning to flag them correctly. What is the difficult part here is that we can have clusters of seeds. And well, when there's a whole cluster of seeds that is very bad, then we want to keep it, because then it will not be trivial to move away from it, right? So the machine learning needs to be recognizing clusters. An extra thing we can do based on this is see, do we have specific configurations that have more or less anomalies? This will give us insight on the physics behind it a bit, let's say. Okay, we tried a few approaches. We tried one supervised learning with support vector machine. DBScan, this is the most interesting one. It's a density-based spatial clustering of application with noise, because it will recognize the clusters. Then we have the local outlier factor. And then we did some post-processing on DBScan as a last possibility, where we applied some, let's say, sanity checks, some thresholds. For example, we say that an anomaly can only lie at the minimum of the maximum of, let's say, the radial scan. If we have two clusters and there is an anomaly in between, well, that doesn't matter. We want the minimum or the maximum out. To check the effectiveness on the algorithm, we need to classify them, which is very typical, of course, in true negative, true positive, false negative, false positives. What is important, of course, is to avoid as much as possible the false negatives, because that means that we missed, the algorithm missed an outlier. And even with human intervention afterwards, we will not catch them again, because otherwise you're redoing the work of the algorithm, of course. But on the other hand, if we get too many false positives, then also we're defeating a bit the purpose of the tool, because then we have a lot of manual work afterwards, which was exactly what we wanted to avoid. So we want to balance a bit these two. So this is how these four algorithms actually perform. This is a logarithmic scale, which is why for the true negatives, we have almost no difference. What is interesting here is that the supervised learning, the support vector machine here, the blue one, has the lowest amount of false negatives, which was, let's say, our goal at least. But it has such a high amount of false positives, this is above 1,000, that it really defeats the purpose. This makes it impossible, actually. This means that we have several false positives per study, so that is too much work. On the other hand, DBScan has a nice number of false negatives, only 2 more than the support vector machine. Less false positives, but still quite a lot. But on the other hand, all 3 of the others, so DBScan and local outlier factor, okay, the binary OR was just, let's say, take the minimum of these 2. They're more or less on the same level of false positives. So this is why we introduced this post-processing, because we noticed that most false positives are easily caught, as I said, because they're in the middle of 2 clusters, or they're so far away, but because the clusters are spread out, it is still within some certain sigma. So we can add some manual cuts. This made a lot of sense. And indeed, after this post-processing, we get a number of false positives that is very low. We're talking about less than 10. So this, of course, we flag as our preferred approach. As I said before, I'm going a bit fast over this part because Gianluca already treated it. Just showing some examples here. So this is DBScan without the post-processing. Green being the true positives, blue being true negatives, red being the ones we don't want, the false positives. Like this one, this is clearly not an outlier, but because all of the other ones are quite densely packed, it is far away for the clustering algorithm to be recognized as an outlier. Even in this example, it's much worse. You see all the red ones here as false positives. Why? Because the blue ones are, let's say, essentially overlaying. Why this happens is, of course, because the algorithm is scanning radially, not the full picture. But if we see the full picture, we would clearly see, well, these are not outliers. Applying our post-processing, however, all the false positives are gone except for this one, meaning that instead of having to manually remove some 10 false positive outliers, there's only 1 here. I took some extreme examples to show the point, but it shows that the post-processing really makes a lot of sense. And then an important check here as well is to see, okay, it catches almost all the outliers, but is it like missing more or less in certain configurations? For example, would there be certain seats where it misses more, or would there be certain angles where it misses more? That is important, because then the algorithm is not really reliable, right? We want, if it misses a certain amount, we want this to be homogeneous, that there are no spurious correlations that are entered. And indeed, this is yellow being the ground truth, blue being our dB scan with post-processing or algorithm, and we see that indeed yellow is always a bit below because we get some false positives. We get no clear angular or seed dependence. So that is good. The algorithm works as we wanted. Up to here. Now, something extra we do with it is actually we can, as I said in the beginning, recognize strong dynamics. This is, I believe, something that Gianluca did not treat in his presentation, so I will expand a bit on that. How can we do that? Well, we can look at specific configurations, look at the pool of studies we have, and only select those that have a certain configuration, and see if that configuration causes more outliers for a certain seed or for a certain angle. Because then it tells us that this is, let's say, a sensitive configuration. It also tells us that we might want to not use that seed in our production studies because it is having too much outliers, so it means that it's too unrealistically bad. So what I'm showing here is this our algorithm applied on all the studies I had available last year, some 4,000 studies, split in between the studies for the LHC and studies for the high luminosity upgrade. And we clearly see that there is a bad seed here at seed 10. And that seed 10 has, on average, 1 out of 3 anomalies per study, which is, I would say, rather high. And so out of 3 studies, 1 of them will have an anomaly. While for the high luminosity case, this is completely not the case. There it is a very small amount. On the other hand, for the high luminosity upgrade, we see that we have 2 bad seeds at 33 and 39, which are, again, not present for LHC. So indeed, we have some dependence on the seeds, which depends on the configuration. That is interesting, but can we disentangle further to see where it comes from? So seed 10 for the LHC, 33, 39 for the high luminosity upgrade. Can we disentangle by looking more specific in these configurations? And yes, we can. We can, for example, start looking at the optics. For the LHC, we have 2 general classes of optics, let's say. Until 2016, the standard beam optics were what we call the nominal one, but in 2017, the ATS, the telescoping optics were introduced. They're different. And indeed, what we see is that this outlier, this bad C10 that we saw, is completely in the nominal optics, where in that optics, so this is for 246 studies, on average, almost each of them had an outlier. So let's say from this, we can conclude actually that when we're doing simulation studies using dynamic aperture for the LHC with the nominal optics, so the one before 2017, then it's better not to include this particular seed because it will give a distorted view. We see also that the angular dependence is a bit different. This is also interesting. This I don't have a clear explanation from the beginning. This could be investigated, of course, but I think there is more to gain from this clear information. We can do the same for the high luminosity optics. There were 3 types of optics, 3 versions that were used in the studies. And also there we can clearly see that the 33 seed, the very bad seed here, is only appearing in the 1.4 optics, where 1 out of 2 studies actually has an anomaly. So then here the message would be the same. If we do high luminosity studies with 1.4 optics, avoid including C33. So avoid including this one, remove it out, get another seed. We see that this 39 is actually present in the 1.3 optics, even though a bit less pronounced because it has a different one here. But this is not a big one. We can see 1.0 as an outlier seed here, but also that one is not that significant. What we also can see is that the angular dependency is opposite. 1.4 has most outliers at low angles, while 1.0, for example, has most outliers on high angles. And then the last check we can do is comparing beam 1 with beam 2, because we're running simulations for both beams, the opposite beams. And also there we can see. So C33, this was the seed in the 1.4 optics for the high luminosity upgrade, is mainly, well, purely for beam 1, while the C39 that we saw before is purely in beam 2. So as a conclusion, let's say to conclude the whole thing about the anomalies, it's interesting to see that we can use the algorithm we developed, the machine learning algorithm, to actually disentangle some dynamics and to deduce that if we use LHC non-ATS optics, we should not include C10. If we do, or at least expect bad values for C10, let's say, If we do the same for high luminosity, beam 1, 1.4, we should expect that values for 33, and beam 2 optics 1.3 and beam 4 and 1.4 C39. To get more information about the angular dependencies, further investigation would be needed, but since we're talking here about a consistent, let's say, dynamics, we see the difference between versus high towards low angles. This is something that needs more investigation. I believe personally it's quite interesting because it's, let's say, an algorithm that is used for something that was not its main purpose. The main purpose being getting anomalies out. An extra application is, well, recognizing dynamics. Okay, let me then come to the main part of my talk, extrapolation. So the main thing is these DA simulations. They're extremely CPU intensive. They're running on the batch system of CERN. There are also some of them are running on Boeing, which is a distributed system where people can contribute their screensaver time to run our calculations. Even then, we don't have that many possibilities. Let's say typically we only achieve 10 to the 5, 10 to the 6 turns, so up to 1 million turns. But 1 million turns is around 1 minute of beam time. Of course, the beam in the LHC stays much longer, several hours, maximum up to 20, 30. I think the maximum in 2018 was 40 hours or something. On average, let's say around 10 hours. So 1 minute is really not that representative for the beam dynamics. If we have highly nonlinear systems, which is of course those that we are exploring, we need some information on a longer time scale. In other words, we need to extrapolate our simulations. Now, luckily, we have some analytic laws from nonlinear dynamic theorems, from the Nekrashev theorem. We can actually deduce some laws that tells us how will this dynamic aperture evolve over time. Now, it doesn't work perfectly, as I said before, so we want to improve this. What can machine learning do for us? Well, we do 3 things here. We can improve the fitting. We can use really a neural network to make the prediction estimate instead of fitting. I will tell you this doesn't work. This is also expected to not really be that efficient. And then the last one is a very efficient one. We can use Gaussian processing to increase the density of the points to get better fits. And that one works really very well. Okay, so what is the model? Well, we have several variants of this model. What I present here will be using model 4. That's what we call this model. We call it model 4. This curly W, this is the Lambert W function, some exotic mathematical function. It's the inverse of x times e to the x, just so you know. But anyway, what is important for the model is that it has 3 parameters, rho, mu, and kappa. Kappa is like defining the curvature of the curve, more or less. Rho is some general scaling, and mu is some let's say, adaptive parameter. For mu, we have some estimation coming from our theory. It's an estimation, so it's not necessarily exact, which is given by this thing. So we use 2 variants. We have 2 variants of this model, 2 parameters, 3 parameters, with and without mu. This model works well to describe the data, not that much to predict it. Here is exactly why that is. You can see here, so black is the data. Red is the fit of the model on the data. We see it's a nice description of the data. However, if you use it to predict and we fit up to half, so up to 500,000 turns, sorry, 50,000 turns, this is 100 in total, up to 50,000 turns, we see, and we extrapolate on the model, that we get actually an overshoot. Of course, this gets worse the more we try to extrapolate. Well, this is not wanted, especially because it's systematic. We can always recognize this kind of overshoot. No, and the problem is, we did simulations up to 10 to 6 turns, even up to 10 to 7 turns, and the problem persists. So there is some problem with the model that it's not really able to catch fully the curvature, actually, and it misses it. We have some explanation for it. We actually discovered that if we do our tracking, including completely the longitudinal component, this gets much, much better. But still, we want to see, can we actually somehow get better predictions? Because if we would draw this as a human, let's say, without mathematical information, we would be able to extend the data. So then the question is, can we somehow teach our fit to also be better at that, be more human? First thing, neural network doesn't work, was expected. This was a try. Now, to be honest, the try was really a basic try, like a back of the envelope, just some standard things. it can probably be improved a lot. But what still remains true is that, of course, neural networks have difficulties giving values for something it is not trained on. So this one was a recurrent neural network, Keras. And you can easily see that here. So red is the predicted data, blue is a ground truth. It is actually set off by this bump here, and it tries to mimic the bump somehow. There were other cases where it was not that bad, but in all the cases it misses. It misses the prediction is wrong. Instead of trying to focus, trying to make something which is not intended for this work completely, we shifted our attention. There are several alternatives. The first one is, can we find optimal weights for the fitting? We have all the data. Can we find a better way to actually weight data points more than others for the fit? This works to some extent, but let's say it's not entirely smart. It just shifts toward the last points, because then, of course, the extrapolation gets better. Now, another thing that could be done is also like use a neural network as a replacement for the fitting algorithm. So here before, it was actually trained on the data itself and then expanding the data as typical for a recurrent neural network. Here, the idea would be actually to train based on several sets of studies where the input point would be one study, let's say the points up to some value, and the output would then be the extrapolation values there. And then we could actually use, instead of the standard least squares estimator, we could use like extrapolation quality somehow. This is not that trivial to implement, and this is something that at some point I still would like to try to do. But it might take a lot of time to actually get this working in a fine way. Also, the way it is presented, the way I say it now, it would not include the information on the scaling law, which is a bit of a loss because we know that the law is correct. So ideally, it would be combining this information in a neural network somehow. There are probably ways to do it with modern techniques. I will come back to that in the end. But we started first by something which was a bit easier to implement, which is a Gaussian process. A Gaussian process using the Gaussian process to increase the density of the points. So getting more points to fit on to get actually a fit of higher quality, better fit fidelity. So for those who don't know what the Gaussian process is, Gaussian processes are what I call Bayesian non-parametric regression. Some people call it a natural extension of linear regression using all the functions. And I'm sure that those people who know Gaussian processes have heard all the functions all the time. So let me expand a bit on that, what that means. So standard linear regression, we all know what it is, and we fit to parameters. Now, what if the data is not linear but is parabolic? As simple, we add a parameter and we go to a squared fit. Now, of course, what happens here is that you need to decide the number of parameters in function of the type of data. What if you don't want to do that? What if you don't know? What if you're not entirely sure? Or what if the data might be spuriously pretending to be parabolic while it is not, or whatever? There might be reasons you don't want that. Well, in that case, you consider every possible function possible instead of restricting to quadratics, for example. That's why for Gaussian process, people say all the functions. Of course, it's not all the functions, that would be unworkable, but we consider classes of functions. So how does it work? Well, in Bayesian statistics, you have the idea where you have a prior, you have evidence, and then a posterior. So you actually draw conclusions from your evidence, combining on your prior, updating it, and getting posterior information. So we start with the prior distribution here, which is assumed to be, of course, drumroll, Gaussian. That's why it's a Gaussian process. Multidimensional, because we're looking typically at higher dimensional data. And it's a Gaussian distribution of function. So it's a functional distribution, if you want. So the distribution of Gaussian is defined by the domain of the data. So we can restrict already the functions that are valid over this domain. And then our Gaussian has an expected value, a mean. Now, it's a functional, it's not a Gaussian, it's a functional Gaussian. So the mean will be a function of the coordinate. And the Gaussian is defined by the smoothness, sigma, the covariance matrix here, which is again a function of x. How does it work in practice? Well, very easy. If this would be initial distribution, we start with an initial distribution of functions. I did not make the drawings, by the way. Here is the source. Or Gaussian, let's say, or prior estimate of the Gaussian distribution will be, well, mean 0, sigma 1. That's the easiest Gaussian we can have, right? Again, this is a functional of functions. And then we add evidence to that. Evidence meaning data points. Okay, adding this evidence, we can actually then correlate this, get probabilities, and make a posterior, which will be a prediction. So correlating the evidence with the initial functions we had before creates this kind of functional behavior. Again, how we're looking to a distribution of functions. Of course, the distribution is going to be exact at the evidence because that the data is known. And this is typically how a Gaussian process distribution looks like. So this will be the prediction. Prediction having two variables, the covariance and the mean. So the covariance is the width. Of course, covariance changes in function of x because it's a functional, and the same for the mean. So this here will be the mean, and this will be the covariance matrix. So this is essentially like a changing Gaussian distribution. This was in one dimension. In more dimension, it gets more difficult to make images that make it clear, obviously. So this is, of course, ideally suited to add density to points because Gaussians, well, nature works with Gaussians. So we have points, we add Gaussians, and we get a higher density over fit. This will not work for extrapolation, of course, because then this thing, you can see the borders, they explode. If we want to go for higher x, this thing will completely explode. So we don't use it for the extrapolation. We use it, let's say, working around it a bit. We use the process to increase the density to get a better fit that will give a better extrapolation. That's the idea, at least. So here's an example. We fit to the extended set. So this is an example of one of the very long simulations we did, up to 10 to the 7 turns. So the green points here are the original data points we have. Then the dashed line here, sorry, the green line here below, you cannot almost not see it, but it's the green dash. This is the fit to the original data. Then the blue dots here are what the Gaussian process adds. Now, this is, of course, not a vertical line. We're just collapsing. So this would be 10 to the 4 up to 10 to the 5 turns. So we're fitting from 10,000 to 100,000 turns, because again, we're interested in extrapolation. And then we make another fit based on the original data plus the synthetic data. Now, they overlap, right? So then the main point can be, why would that be better? Because the two fits are exactly the same. Well, they are not. We're going to look at the mean squared error of the fit. Now, of course, mean squared error of the fit only to the original points. Of course, the mean squared error will be better if we compare it to the synthetic points as well, because, well, you have more points, so the fit will be closer to these points. No, the fit improves if the mean squared error with respect only to the original points improves, meaning gets smaller. Then we can say adding synthetic points actually gave a better fit. And that's what we're going to test now. So we choose a random study from our long-term simulation studies, which has at least 500,000 turns. Then we sample from 10 to the 4 to 10 to the 5 points, 50 of them. So to be clear, I didn't mention it, the Gaussian process distribution, of course, is always evaluated at certain points, which you just choose arbitrary. If it would be a true functional, as I called it, it would be continuous, but that would not be applicable in programming languages. So it's evaluated at certain points. So we choose 50 points between 10 to the 4, 10 to 5 turns. We use a Gaussian process to assign the predictions to these 50 points. And we do this 500,000 times for the same study. So we make 500,000 different Gaussian process realizations. And then every time we fit and we compute the mean squared error of the fit, again, with respect to the original points. We do this twice because we had two models, one with 2 parameters and one with 3 parameters. And we see how that looks like. Now, what we want to know is how many iterations of the Gaussian process would we need to get one that is really making the fit a lot better? Because of course it's a bit random. It's a random sampling. It's a Gaussian sampling. So not every Gaussian process iterating is going to make the fit that much better, or maybe even worse. So what we are going to do is we going to define this value, which we call the rescaled distance in the mean squared error, and it's going to compare the minimum of the Gaussian process up to some point. So up to some point that is smaller than the 500,000 realizations we made, and we compare that, we subtract that from the average of all realizations, and we scale it in function of sigma, so we can see how far are we in this distribution. in this distribution, sorry. And another thing, another value that we can use as an estimator is the relative gain, is how far is this minimum MSE now from the original MSE. So how much are we gaining actually by using this minimum rescale to the original. So this is how it looks like for a 3-parameter fit. This is the distribution of the mean squared errors of the 500,000 realizations. And this is the evolution of this epsilon min, so the rescaled one. And we can see that indeed it goes down quite fast in the beginning. Then if we may make 10 iterations, we are very close to, well, 0, meaning here. Of course, we take the minimum, so we're always going down. After 200, 300 iterations, we're at -1 sigma, so we're probably here. After 1000, we get slightly lower, between so 1 minus 0.5, 1, something like here, probably. Then we will need more than 10 to the 5 iterations really to get even better. So then one can argue the small gain here that there is by adding 2 factors, 2 orders of iterations is probably not worth it. Looking at the 2-parameter fit, we can see 2 things. Well, first of all, the mean squared error is much higher. If I go back here, the average is around 0.0033. And here it is at 0.0061. So the average is double as high. I mean, squared error is double as high, but that makes a lot of sense because it's a 2-parameter fit. A 3-parameter fit will almost always be better than a 2-parameter fit. Well, because you have more things to tune. It doesn't mean, of course, that this is good because, well, you can keep on adding parameters. There is no sense in it if they're not physical. So it's just to say that it's expected that the 2-parameter one has a higher mean squared error. But what is also important to see is that actually the spread of the iterations is much higher. Compared here, we have a spread of full width half max will be something like 2.5, 3. And here it is more like 5-ish. So the spread is much higher. Why is that important? Well, it means that there is much more to gain by doing more iterations. And we can indeed see that here it falls down much faster. You can actually, with 10 to the 5, we're already at -3 sigma, so we're already here, while here we didn't reach it. So in a sense, that also makes sense, right? In a way that makes sense. The 2-parameter fit, of course, will have a worse mean squared error than a 3-parameter fit, but there will be more to gain because it is worse. Yep. So here is some data, some small table. Now, what is important here is I included now this relative gain. This is, as I said, this is what we gain compared to the original fit without any Gaussian processing. And it's different than the conclusion that we would make from it. So this epsilon min after 100 iterations will be -1.02. And the epsilon after 1000 will be -1.3. So that's 30% better. This one actually doubles for the 2-parameter fit. Going from 100 to 1000 iterations doubles the, let's say, the quality. However, if we look at the relative gain, there is not that much gain. This was at 61% better, and this is 62% better. Why is that? Well, because epsilon min is only rescaled to all the iterations. It does not take the effect of one iteration into account. And of course, let's say, that's something you should include because, of course, the first iteration already gains a lot for the 2-parameter fit. So this is the one that we should make our decision on. And based on that one, we would say, actually, after 100 iterations, we have already quite a lot of improvement on the quality of the fit.
Okay.
Now, what was the question? Okay. Okay, this was about the fitting quality. Now, what it is all about, of course, is the extrapolation. And the reliability of the extrapolation. So for this one, we have the 6 studies we did with 10 to the 7 turns. That's already a lot. That's 900 seconds of beam time. Well, it's not a lot on the big scale, but it's much more than what we had before. What we do here is we fit up to some Nmax that is smaller or equal to 10 to 7. So we let it grow. We include always more and more points. And then we see actually how is the value at Nmax improving. So let's say the first fit would be at probably 100,000 turns. And then we see what it tells us as an extrapolation value for 10 to the 7, right? And then we go up to 10 to the 7. So of course it will go down because we have an overshoot. And of course the error, the delta dA, which is, let's say the error in extrapolation also go down. However, if we only would look at the value at Nmax, then it is not very robust from a statistics point of view, because this point has some fluctuation as well. So we're actually going to see how the MSE, the mean squared error, will go down, because then, of course, if the overall fit improves, also the extrapolation improves. Again, mean squared error over all points, up to 10 to the 7, all non-synthetic points, not including Gaussian processing. So we fit, for example, up to 10 to the 5 turns. We calculate the mean squared error over all the points we have 10 to the 7. That's our baseline. Then we do the same with 200 GP iterations. So as I said before, 100 seems enough. Let's take 200. Why not? It's only 100 more. Where we increase the number of synthetic points while we grow. That also makes sense because we're fitting more points. So we start at 500,000 turns, not 100,000, where we add 75 synthetic points, and we go up to 5 million. So that's half of the 10 to the 7. And there we use 750 synthetic points. How does it look like? Well, this is for the 3-parameter fit. We see that indeed the mean squared error goes down, and it saturates here, which is nice because it tells us that, well, of course, you expect it, because the closer you get to the final value, the better the fit will be. But it also tells us that if it saturates, we could go up to here with our simulations and get a reliable value for here. Now, so we could go up to 3 million turns to get a reliable value at 10 to the 7 turns. Now, if we do that with the GP fit, we see, first of all, it improves overall, no matter how far we go, which is good. It would be very unreliable if for some points it actually doesn't make it better. But also we see that the saturation happens earlier. And that is, well, a pretty good result, because it means that we don't need to go that far. So 10 to the 6 is probably not good enough, but we can go up to 10 to the 2 times, so 2 million turns, and get a value that is actually already very relevant, that is very representative for the 10 to the 7 turns. So using Gaussian processing, we can actually make our extrapolation double as reliable, let's say. For the 3-parameter fit, for the 2-parameter fit, well, as before, there is more to gain. It was wider, remember? So there's more to gain, so the effect will be even bigger. The saturation happens a bit later. So I would argue probably going 2.5 to 3 million turns to get the value at 10 million turns. So yeah, exactly. So the saturation appears around 2 to 5. 5 is very, very good. 2 is almost as good. So 2.5, let's say 2.5 million turns will allow you, using the standard analytical model we have with Gaussian processing, 200 iterations, we will get a reliable extrapolation to 10 to the million turns, which is a pretty good result. Now, this was one study, right? 6 studies, the 6 10 to the 7 studies that we had before. So before we can make this in a strong statement, we have to check the reliability on a larger data set of studies. I have, today I have more studies. At that time, I had 3,000 studies that were, let's say, reliable enough to be tested in this way. All of them were LHC, so standard LHC and High-Lumi. And they were all kinds of operational conditions, all kinds of non-linear errors and this kind of thing. So we have a broad sampling of studies. We have a fit that goes up to 10 to the 5, 100,000 turns, and we extrapolate to 10 to the 6. Only 50 Gaussian processes here, right? Well, to gain a bit on time. If this is good, we know that 200 will only be better, right? So this is some kind of bottom line. Okay, so we look at the distribution of the mean squared errors of all the studies, these 3,000 studies. And then we compare them the same distribution when we add the Gaussian processes. So before you say, oh, this looks almost the same, it is not, because we have a much higher core here, almost towards 10 to the 3, where it here was 200. So from 200 to 1,000, meaning that actually the distribution is like thinned out and get much more very low mean squared error. So we really get like a push down of the mean squared error on average. We can make that in a stronger statement by looking at the delta MSE. There are still a few studies actually that get worse with the Gaussian processing. Now, of course, in reality, it's very easy to add a check that you don't use the worst result, right? So, but then let's say this would essentially just mean here we cannot use the Gaussian processes. We literally have 1, 2, 3, 4, 5 studies, 6, 7. And a bit more here. Okay, let's say, I don't know. Let's say 1% of studies, less than 1% of studies, where the Gaussian processes at 50 iterations won't work. there is a high chance that at 200 iterations it already works, or that this number goes down quite a lot. For quite a lot of studies, we have some small gain, and we have actually up to 0.02, which is a rather okay gain, I would say, on the MSE. The same for the 2 parameters, where as before there is much more to gain, so it becomes much clearer where actually we lose all the high mean squared errors here. And the same for the delta, where we have less extreme cases where it didn't work. Again, only 50 iterations, result will be much better at 200 or even 1000 iterations. So here again in the table, we can clearly see that the overall MSE reduces. We had for the 3 parameter fit an original mean of all the studies of 9.93, 10 to minus 3, it goes down to 7.78, median goes down, standard deviation goes down. And for the 2 parameters, as before, much more to gain. It halves literally, median goes down as well, standard deviation is even 5 times smaller. Very clear improvements by Gaussian processing, especially for the 2 parameter fit. So I think we can safely say this is success. All right, that's the end of my talk. So conclusions, some part about the anomalies, very efficient detection. What is interesting, I believe, what is rather interesting really, is to use it in an alternative way to recognize bad seeds and to decide not to use these anymore. It's difficult to use a neural network to extrapolate in a reliable way, but we knew that. We didn't expect much there. We have a very efficient way to improve the overall fitting quality, which is Gaussian processing. Now, there is, of course, still lots to do. There is still lots to try. We could make anomaly detection centralized to get some kind of centralized supervised learning, so reinforcement learning, so that it improves itself. Because now we had a training set of 300 to 500 studies, which was, of course, well, a lot of manual work, because then it's a human flagging the outliers. But of course, by reinforcement learning, by the human that is verifying and approving or not the flagged outliers, the algorithm can improve itself. So that would be a very efficient way to get it more centralized. We tried, and we can continue trying, to use supervised learning on the fitting weights. As I said, we did some back of the envelope try. It was doing things which were a bit predictable, but this can of course be done much smarter in a way that is probably leading to something that is interesting. What I think is very interesting, we can improve the prediction algorithms on high precision data, training them study by study. Every study would be 1 point in the training set, and then actually see if machine learning can unravel, like if it can unravel what is the general structure of the evolution somehow, would be even stronger if we can add the information from the scaling line to that. And then as a last one, we can actually explore modern algorithms, which are alternatives. There are, for example, since 2018, there exist NALUs, neural arithmetic logical units, which actually have a lot of promise for extrapolation, literal extrapolation, because what is happening there is the neural network is trained to recognize the functional structure of the data. And of course, if you know the functional structure, you can extrapolate. This is in contrast with a normal neural network, but it's just like looking at correlations in the data. Why the NALU will really look at mathematical functions. Interesting times, interesting things. And that was it. Thank you.